Dr. Huckabee here again. This lecture was brought to you through a repurposing of a lecture from last semester. It finishes our work with Chapter 2, so congratulations, you made it in Chapter 2. And it talks a lot more about resonance and how we talk about the patterns that form and resonance hybrids. So without any further ado, here is your to-do list. Visit Canvas as always. Do your homework assignment that's due on Friday. Work Chapter 2 problems. You should be able to do them all after this video and begin reading Chapter 3. Good luck. Great. The fourth type of resonance in this series, the fourth pattern here, is whenever you have a double bond between atoms of different electronegativity. So we'll just say pi bond between two different atoms. All right, hopefully you can read my writing. If not, just yell at me later or something. Okay, so pi bond between two different atoms of different electronegativity sounds complicated, but it's really not. This is like when we have a carbonyl, okay? What do you have between the carbon and the oxygen? You have a pi bond. So that's really all we're talking about. So when you have a system like this, you can, I want the red, there we are. You can move the electrons from the bond to lone pair and make a structure that looks like this. And we'll give it our resonance brackets, as always. Now, you might say to yourself, the doubly charged structure looks pretty bad compared to the neutral one, right? Who would draw two charges instead of just two happy neutral atoms? And for the most part, you'd be right. Because if you did all the math and you found out where the electrons were, and you could weight both resonance structures to their probability or to what the molecule really looks like, you would find out that in all actuality, the vast majority is in this one. But there is still some character of this guy here. And, oh, I did all the charges the wrong color again. I have a problem today. There we are. Okay, reds and blues. We're all happy again. All right, and then the lone pairs to come back down. Okay, so you do have some of the doubly charged species here. And that actually is one reason why this type of pattern is really special in organic chemistry, because while you still consider the carbonyl structure to be that neutral, the neutral structure with a pi bond between the oxygen and carbon, you also have to think about the structure in this way. You have to think about it as, yeah, you have the double bond, okay, but there is substantial partial positive and partial negative between these two, meaning that the oxygen would rather take that pi bond and kind of keep it for itself like in that second structure. But they're still going to share them. Even so, if push comes to shove, the oxygen will take more of those electrons, and the carbon will give it more. So the carbon has a partial positive charge on it. Doesn't sound like anything special right now, but again, this is one of the biggest patterns to learn in organic chemistry because so many reactions start at this point. All right, the last one that we'll talk about is one that we'll touch on some. Again, if you've seen the homework, you will know that this type of resonance is one we'll deal with a lot, and that is pi bonds in a conjugated ring, right? And essentially what this means is, if you remember what conjugation means, it means alternating series of single and double bonds, and them being in a ring would look something like this. I'm not sure how many of you are familiar with the structure benzene, that is C6H6, which is what we have here. But this is benzene. It is totally conjugated, single, double, single, double, single, double. That's what we're talking about. And you can make a resonance structure of this molecule that alternates where the bonds are, but does not break the conjugation. You can go back the other way, just like we have in the other structures. And have resonance kind of like this. Conjugation is a special way to increase stability in molecules. The more conjugation you have, the more stable and low energy a molecule will be. So a molecule like benzene is very special. We have it all over the place in chemistry. There are amino acids that are built around benzene, phenylalanine, tyrosine. Both of those are based on benzene. Dopamine, serotonin. Tons of molecules have benzene rings in them, and even more have conjugation inside of a ring like this. So being able to look at this pattern and just draw some arrows, draw some electrons moving around is a very useful thing. All right, so now we know kind of like what types of patterns there are, because we're going to talk about 5 in this class. You got them. They are what again? They are allyl anions, right? Allyl cations. You have lone pairs next to a positive charge. You have pi bonds between 2 different atoms and pi bonds in a conjugated ring. You will be able to use all 5 of these throughout the whole semester and next semester as well. But what you really want to know is why, right? Like, why does it matter? How can we use them? How can we know which structures are better? Well, it's not enough just to know the patterns. You also need to know some rules for what makes a structure better, right? Because we could look at some and say, yeah, that's a bad structure. That first structure we saw, the first resonance structure, that's just a bad structure. It'll never happen. But what if it gets a little more complicated? What if you have to say between the 2 benzene rings what the best structure is? What if you have to say between these 2? I mean, these 2, you guys all figured it out pretty quick too, but it's going to get more complicated from here, as you might imagine. So we're going to come up with a couple simple rules that will help you know how to build your resonance structures and how to rank them. The first rule: you want to make the most possible filled octets. You remember octets mean that every atom has its 8 electrons, every atom is happy. You want to give every atom 8 electrons if possible. Even if you have charges, do it anyway. So one example, let me start over. I don't like how I was drawing that one. Here we go. There we are. That's better. Positive charges are blue, right? There we are. And I'm missing the lone pairs. Okay. All right, so in this structure, we don't have an allyl, so we don't worry about the first 2. Do we have a conjugated pi ring? No, I don't see one either. I'm going to put these rules here, and we'll just go through them each time. Do we have pi bond between 2 different atoms? No, but we do have a lone pair next to a carbon cation, right? All right, so let's start with that. We're going to do a lone pair next to a carbon cation, and that means just moving the lone pair down into the bond. So let's finish the resonance drawing here. And the oxygen still has a lone pair, But if you remember, an oxygen with 3 bonds and 1 lone pair has what charge? Anybody? I heard some murmuring, but I couldn't really hear it. +1. I heard a +1. That's right. Does everybody remember how to calculate formal charge? Yes? Okay, good. Between these two structures, okay, both have a charge. However, you might notice that one is substantially different than the other. Okay? If we look at each carbon, so let's start here at the end. This carbon has how many hydrogens bonded to it? 3. Good. I heard and saw some 3s. It has another a carbon-oxygen bond, which makes 8 total electrons. So that one's happy. Oxygen, 2 bonds, 2 lone pairs, 8 valence electrons, right? So it's fine with that. This carbon has how many hydrogens bonded to it? Okay, I'm hearing some 2s. Does everybody agree 2 is the answer? Ooh, so I'm seeing some dissent. All right, I'm seeing some 1s as well. Remember, in line bond drawings, if a carbon has a positive charge, that takes away the number of overall CH bonds, right? So that means that this carbon has 1 CH bond here, which gives it how many valence electrons? 6. 6 valence electrons total, less than an octet. And the other carbon, again, has how many valence? Yeah, it has 8, exactly. Okay, in the other structure, we have the same 2 8 valence electron carbons on the end, so we won't waste our time talking about those. This oxygen now, 3 bonds and a lone pair, that still makes 8 valence electrons, right? Yeah? And this carbon, how many CH bonds does it have? Still the 1, okay? Which means it actually has a full valence bond, or a full octet now. So that means if you were to look at these two structures, you could say 100% sure that this is the better structure, the major contributor, and this one is the minor contributor. So whenever you're thinking about what this molecule is really like, what it's looking like, where the electrons really are, it's going to have much more of this character because of the filled octets than the first character. Which means in this structure, the oxygen will have a partial positive, right? Because it won't be a full positive charge, but it will be part of it. The second big rule is one that you kind of already got the feel for, I think, and that is less charges if possible. And that means exactly what it sounds like. The more neutral you can make the molecule, the better. If we draw a structure that looks like this formamide, or formamidine, we can also make resonance structures that look pretty similar to what we had before, right? Because we don't have a conjugated ring. We don't have any lone pairs next to a carbocation. And we don't have an allylic cation. But what do we have? The allylic anion, and we also have the pi bond between 2 atoms of different electronegativity, right? Does everybody see that? The allylic anion comes from this lone pair and this double bond, and then the pi bond between 2 different atoms is here between the carbon and the nitrogen. Where I'll see that, I see a lot of heads nodding, no heads shaking. This is a good sign. We're all here together. Great. Now, if we take this lone pair and we move it down, what is that going to do to the carbon? Is it going to have a better life or a worse life in this case? Well, yeah, a lot worse life. It's going to be much less happy. So what we're going to have to do is move other electrons along with that. So let's move these onto the nitrogen. And we'll redraw the structure like this. All right. I'm finished, right? That's all there is to do? No, good. I heard a no. Look at that. What do I need to do? Do I need to add something? Yeah? Do I need to add a positive charge anywhere? On a nitrogen. I heard nitrogen, so let's do that. Here, right? No. Okay, it's up here. Great. And it's blue, which you know makes it right. What about the other nitrogen? Is it charged or is it neutral? All right, here's some charge. Oh, I hear both. Charged, negative. That's right, I heard both. Okay. Negative. So you see that the beginning molecule was neutral, the end molecule is neutral, so it seems like, you know, maybe that's not against the rules, so to speak, because at least the charges are the same. But which structure is better? I mean, obviously it's in this special rule about less charges is better, right? So probably the first one is better. But it's very illustrative because neutral is always better when you're making one. You know, maybe in some special cases like above, the positively charged oxygen, which is weird, is favored. But in general, when you're making a resonance structure, if you're choosing between neutral or charged, the neutral one should be the major contributor. Okay, we're going to learn a lot of stuff this semester. Maybe you'll see an exception, but this is the rule. All right. So one reason why I wanted to, or one reason why I mentioned before that you wanted to do one arrow at a time if possible is because we didn't actually draw all of the possible resonance structures here. Right? Does anybody see that? There's one resonance structure we did not draw for this formamidine. And the reason why is because we were very excited to do these two together. If we did one and then the other, we would have seen it. If we would have drawn this first one and then the second one, we would have seen it. Had we taken this bond, kept it up there, we would have seen a structure that looks like this. So now we have our negatively charged nitrogen, but instead of the positive charge being on the other nitrogen, now it's on this carbon. Okay? So the question is, between these two, can you see which structure is better now? Yeah? In fact, if this is the major and this is the minor, this is like the minor squared. This is not the best structure. I mean, it doesn't break any rules, but you notice that the carbon doesn't have the octet. Same number of charges, carbon has 6 electrons instead of 8, so it's just not going to be as big of a contributor. And I said there were going to be 2 rules, but I'm an organic chemist, so I feel like it's okay if I lie. There are actually 4. The other 2 are they're less important, but they are still things to consider. Sorry, I dropped my papers on the way, and I got all scattered. And so I'm very paranoid that I put them in the wrong order, and I just get all jump around. But I think they are, in fact, in the right order. So number 3 in these rules to draw resonance structures by is that if you can, you want to put negative charges on the more electronegative atom and positive charges on the less electronegative atom. Does that make sense? Just me saying it like that. The atom that wants charge the most, you want to give it the negative charge, and the one that wants electrons the least, you give that one the positive if you can. Okay, so we're going to call it most electronegative minus and least electronegative pluses. All right. Okay, but seriously, how bad is it? Can you guys read this, the electronegative there? If not, it's okay to say no. Okay. I'm not seeing any shaking heads. If you just don't want to say anything, email me after class. I'll try and get better at handwriting later. All right. So what this means practically is that, again, if we go back to one of these structures where we have a carbonyl, okay, we can reason through, again, why the charge structure, while not the major contributor, is still one that we can look at. Because in that structure, if you remember, the electrons flowed from the pi bond up to the carbonyl oxygen, making a formally charged carbocationic center and a negatively charged oxygen, right? But what about in this case? So this is the carbonyl we were looking at before. If we instead are starting with this negatively charged carbon next to the carbonyl, perhaps you, in all of your organic chemistry wisdom, already see that this is like an allylic anion, right? Oh, good. I see some people who are happy to have found that. If not, keep practicing, you'll find it. If you have an allylic anion type of carbonyl here, it gets a little more funky. And what we'll do is we'll draw, again, one arrow at a time so we can see all 3 structures. I gave you the answers 3. And then we can assess which structures are better than the others. So if we first move, again, the pi bond up to the oxygen, we'll just do this. You get the same negatively charged oxygen. You already had a negatively charged carbon down here, but you have now positively charged middle. And this might look very familiar to you from that structure we said was so bad in the beginning, right? All right. Now, let's move the electrons one more time, and let's put them in between the 2 carbons. To make a structure that looks like this. With a negatively charged oxygen, and now you have a double bond between the 2 carbons. So let's take a broad look at each of these 3. Okay, each of the 3 has an overall -1 charge. Does everybody see that? We still kept the original structure's -1 charge. Is there a worse of the 3? Yeah? Everybody sees the one that just looks the worst. Do you remember our rules so far? We had what? Most filled octets, fewest charges. So already you can decide that one of them breaks one of those, or not breaks one of the rules, but is a violator of one of the rules, right? The second structure here, it has 3 charges. So probably that's going to be the least good option. Even though it's valid, and you can draw it, and it's fine, it's probably the least good, right? So we'll just put this one as number 3. All right, what about between the first and the third? This is why we're putting this structure under most electronegative atoms get the negative. Because instead of drawing this structure like here in this first one, where the negative charge is on the carbon, what it really looks like, if you could do the weighting again mathematically, is the third structure. Okay, so the minor contributor is the first structure, and the major is the third. And this happens because the oxygen wants the negative charge more because it is more electronegative. Does that make sense? Yeah, I'm seeing some minutely nodding heads. That seems good. All right. Last, number 4, and I promise this actually is the last rule here. It's one that we haven't really mentioned, and that is that you can have a tie. You can have 2 structures that are equally as good. Like if you go through these rules and you say to yourself, I don't know, they seem like they're just as good as the other, then they might be. It's possible. So ties can happen. And this is a very important rule in organic chemistry because some groups just intrinsically have multiple structures that are the same. I don't know if you thought about it, but this nitro group we put here in the very beginning, that has the same structure for, well, I guess technically it's the same bonding. What is it? You would call those 2 different structures that are symmetric, I guess. But you couldn't tell those 2 apart if you were trying to say which was better, right? And you have molecules that do this all the time. And that, like, one example is this one here. It's called a carboxylate. And you could imagine that you have one arrow moving up to make now, oops, sorry, this is a negatively charged oxygen, right? That makes 2 oxygens that have a negative charge because they have 6 valence electrons. Oh, it's a red. Because they have 6 valence electrons, or 6 lone pair electrons and 1 bond, and then a positively charged carbon in the middle. Okay, so that's one option. Or you move electrons from the other lone pair down and make a structure, oops, bless you, that looks like this. Okay, so again, looking at our rules, one of them is much worse because it has more charges, so we'll just go ahead and get rid of that one, right? Now we're looking between 1 and 3, and I don't know about you, but I can't see a difference. This carboxylate type of resonance is pretty special because you end up with 2 resonance structures that are identical, which means when you're really thinking about what the electrons what the electrons in this part of the molecule look like, it's not like these 2 structures. We've been building to this point, right, where we're really ready to talk about drawing what the molecules look like. And in this case, we draw something kind of special. Called a resonance hybrid. Okay, this is a way for us to say in a concise drawing what the overall resonance structure may be. And there's some positives and there's some negatives here. One positive is that you can do all the stuff we just did with this carboxylate resonance structure in one, right? It's a lot faster. Maybe you can communicate more easily. But a big drawback is that it's less precise. You know, maybe somebody's looking at how big you were drawing these partial charges or something, and you lose some information there. So like any formalism, you can use it sometimes or not. I prefer to write each structure out, because at least then you can say if one is the major contributor or the minor, but your book does make a good point that a resonance hybrid has its place. And before we move on from how to choose structures, just remember, if you are faced with a dilemma, for instance, in this amide bond, of which structure is best, just be like Drake and choose the right one, right? Okay, so we're talking about resonance hybrids, and this is again, OChem is a foreign language. How to speak OChem. Resonance hybrid is a way to put all these ideas together. You're trying to draw it in a way such that somebody can understand it quickly. You might remember, oh, that's not where I wanted to put that, is it? Oh, it was. Good for me. Oh, no, maybe I did get them mixed up. No, here they are. Okay, no, we're fine. Nobody panic. You might remember that we talked about resonance hybrids before in this example that I'm really beating to death, this allylic cation. Remember we said that there were several different resonance structures you could do. We could move around the electrons, blah, 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 drawn this 5 times. But we could also draw a resonance hybrid that described this electron movement. This is blue. And that structure looked like this, right? Where you were trying to share the positive all along all 3 of those guys. You also might notice that in both of these cases that we were just talking about, that the atoms that we're sharing electrons with are the same. You know, because we're going to start somewhere easy. But what if they aren't the same? And now you're thinking about an electronegativity difference across this shared system, right? And that's where we have to use this formalism of resonance hybrids to its best, to its most elegant usage. Because you can think about a molecule with this structure, as we just saw it, and we just talked about it, the oxygen wants that negative charge. Well, we remember, because we just worked this problem, that there's a second resonance structure that's also valid, where you move 1 electron down in this bond over onto the carbon atom, to make this structure, right? Before I go on, does anybody remember why I draw the hydrogen here on the carbonyl? Yeah, I'm seeing a few nodded heads. It's because in bond line drawings, right, on carbonyls, you always put what is bonded to the carbonyl. You will never, ever see a carbonyl on my test. You might in the book, because some people are interesting folks, that in the book they might write instead this. Okay, and their logic there is that you're supposed to remember in bond line structures that all CH bonds are implicit, but you actually lose information there. So in this class, in these tests, you will always see the H drawn. Okay, moving on. Between these two, there's an electronegativity difference. And we already know that the oxygen wants the electron more, and it is in fact the major contributor. But what we're trying to talk about now is how to condense all of this information into one resonance hybrid. Well, you would draw that very straightforwardly like this, where they're sharing the electrons again, and it's an overall negative charge, except, and this is the part I really don't like about the hybrids, you would just try to make one look bigger than the other and describe it that way. It works. You can do it. It's good to be aware of. Right. Okay. So we are almost out of the realm of only resonance. The last thing to talk about is something that you all dealt with in your last homework, and that is the idea of knowing whether something is localized or delocalized. We talked about it a bit with conjugation, where you have alternating patterns of single double bonds, and that means that pi bond electrons are shared, right? We've been talking about this really this whole time, right? Because you can't have movement of pi bond electrons unless they have conjugation, right? Unless they're next to each other. So really to kind of hammer this down, you can explicitly say whether electrons are localized or delocalized. And it's now that we've gone through all of these resonance structures, I feel like it is a fairly straightforward way to identify where the electrons are. Because now I'm sure all of you can look at certain molecules and know whether the electrons are on the atom or delocalized throughout a larger system. Right? I could probably just draw whatever structures I wanted up here. And without maybe even giving too much mention of them, you could probably say which pi electrons were next to each other, or were in conjugation, which ones are localized, which ones are delocalized. And I could probably even make them fairly hard, and you would probably know. Because all we're talking about is conjugation, and if you can make a resonance structure, the electrons are delocalized. In this first amine, what resonance structure can you draw? You can't. So those electrons are localized onto that nitrogen. With this amide, we said amide bonds a few times now, the electrons on the nitrogen are delocalized, right? Because we have this type of allylic anion structure. The nitrogen lone pair can come into this bond. This is stuff we've been talking about already. The only one that might trip you up is something like pyridine, these pyridine nitrogen electrons. But you had a problem like this on your homework. And I'm pretty sure that a lot of you got it right. So really quickly, I'll just say why the pyridine electrons on the nitrogen are localized. And that is because, see if I can draw this. So here's your pyridine nitrogen, and you have this first bond here. Oh, I'm not an artist. Okay, that bond, 2, 3, 1, 2, 3. Okay. Oh, so bad. Yeah, pretend that looks good. This conjugation in the ring means that all of these pi orbitals are all participating in the same conjugated system. But that's not the electron pair we're talking about. We're talking about the nitrogen pair. And that actually comes out in the plane of the paper. Because they are sp2 hybridized electrons, like we remembered from the homework, they are at 120 degrees from the other carbons in the pyridine ring, and they are not participating in the pi system. So as far as those electrons are concerned, those are just nitrogen electrons. You'll see later in the course that it gives pyridine some special properties, but it's a really weird case of localization.